Hi, I'm Grace McLeod, a PhD candidate in the Hansen Group at Florida State University. I'm excited to share one of our recent publications in the Journal of Physical Chemistry C, Differentiating Intra-Assembly and Interlayer Energy Transfer in Metal-Ion-Linked Multilayers. Metal-Ion-Linked Multilayers are an attractive architecture because of their modular and stepwise assembly. By simple assembly design, we're able to control the direction of energy and electron transfer to perform singlet fission and photon up conversion. Much is already known about the metal-ion-linked bilayers, but because the assemblies aren't in a rigid environment, some motion and reorientation is expected. So we still don't actually know the surface binding angle or relative orientation. Additionally, with this study in particular, we set out to understand whether interlayer or intra-assembly communication was predominant. Intra-assembly energy transfer is what we typically think of when designing these systems, where two linked molecules communicate with one another. Interlayer energy transfer may also be occurring depending on distance and orientation of donors and acceptors, and is defined as energy transfer between two unlinked molecules. Additionally, we may observe some cross-surface migration of excited states. To isolate intra-assembly energy transfer, we synthesized an inert spacer to dilute the surface. It's structurally analogous, but photophysically inert within this system, so it serves only to occupy surface area on our metal oxide thin films. Additionally, we're using a terphenyl porphyrin chosen to maximize the distance between our chromophores in order to slow kinetics as much as possible, and an anthracene derivative. These are well studied in our research as a donor-acceptor pair for energy and electron transfer. To start, our samples are prepared by stepwise soaking of zirconia thin films, first in a co-solution of anthracene and spacer, followed by a zinc linking ion solution, and finally a porphyrin solution. The resulting bilayer formation can be observed by UV vis, where the black trace clearly shows that both anthracene and porphyrin features are together in the bilayer assembly. To confirm spacer loading, because its absorbance is relatively high energy, studies were performed on quartz slides of zirconia. Here we can see both the spacer and anthracene features in the red trace, indicating they both load to form the first monolayer from a co-solution. The loading behavior of the spacer is described by a Langmuir isotherm fit shown at the right. To conform uniform dilution with the spacer, however, we studied the molar percent of anthracene in its co-solution with spacer, and the resulting final surface coverage of anthracene on the thin films. Through this method, we were able to consistently get 100%, 60%, and 30% surface coverage of anthracene. Notably, 100% total surface coverage was confirmed in samples with spacer by multiple dye dip tests following loading. This resulted in no further binding to the treated metal oxide films, regardless of the percent anthracene coverage. With dilute samples in hand, we began energy transfer studies, first via time-resolved emission of anthracene in a bilayer. When excited with 360 nanometer light, anthracene emits at 460 nanometers. However, in the bilayer system, fret from anthracene to porphyrin can also be observed by a decrease in lifetime of emission. As the surface concentration decreases, so does the emissive lifetime of anthracene. This indicates that energy transfer efficiency increases as dilution occurs, indicating that we may be decreasing cross-surface migration in the dilute samples. Similarly, we studied the emission of the porphyrin following direct excitation with 512 nanometer light and monitoring its emission at 675 nanometers. In the bilayer, triplet energy transfer may occur to the anthracene, which will similarly decrease the radiative decay lifetime as seen previously. Ultimately, the rates and efficiencies of triplet energy transfer are unaffected by varying the concentration of anthracene on the surface. For further understanding of the energy transfer events on a short time scale, femtosecond transient absorption was performed. Shown here are the individual components of the bilayer and their spectral features at varying time delays following their direct excitation. On the left, anthracene is shown, and on the right, the porphyrin. Bilayers were investigated by exciting anthracene with the 360 nanometer pump and monitoring at time delays out to 7,500 picoseconds. When comparing the three bilayers, each of a different concentration of anthracene, their spectral features are largely unchanged. We were particularly interested, though, in the rise time of the porphyrin excited state absorption at 460 nanometers. Again, this was observed by exciting the anthracene and monitoring the porphyrin feature, which should only arise due to energy transfer. So taking a closer look at these kinetics, the rise time by energy transfer from anthracene to porphyrin is really the same among all dilutions. This is shown here with a porphyrin-only control, the red trace, being directly excited, where the rise time is within the 250 femtosecond IRF of our instrument. So even at faster time scales, energy transfer rates are unaffected by concentration changes. The main takeaways from this project are that at low surface concentrations, we did in fact only observe intra-assembly energy transfer. At all concentrations, this is the predominant and fastest process observed. And these conclusions position us well to further investigate the metal-ion-linked multilayer structures, as we've determined the mode of energy transfer regardless of many possible orientations and concentrations. Read more in the Journal of Physical Chemistry C. The DOI is shown here, along with our cover art for this issue. Follow us on social media at HansenFSU.